Okay, let's start recording. So welcome everybody to the afternoon session. Got the OBS Studio recording. Can you switch on to me?
It is on you.
Okay, it's not picking that up exactly. I've got good speed here. I've got at least 50 meg. So we're going to go to talk about stepper motor controllers. Stepper motors are what we use to generate precision motion here in our system, like the 3D printer and larger machines. So that's a ready off-the-shelf solution that we can incorporate in the modular design language. So what we need to know about designing for stepper motors and driving them is where to source them and then how to drive them. So the ramps board on a universal controller already has small stepper drivers for small stepper motors. And what are stepper motors? Let's start with some definitions of there's a good diagram on Wikipedia actually. So stepper motors are devices which, let's put up stepper motor image of a standard stepper motor. So these are stepper motors images. You can get these everywhere. We use NEMA 17 size stepper motors. The NEMA rating, like 17, 23, 30, 34, it refers to the inch size between the size of the mounting plate. NEMA 17 being the smallest. I think it's 1.7 inches, I believe, is it across the face, or it might be next to the two holes adjacent to each other. But stepper motors look like this. They have internally, if we look at the diagram, what a stepper looks like on the inside.
Do you have a screen share?
Let's share it. Sorry. Okay. So here's a diagram on Wikipedia. Here's a diagram of what a stepper motor looks like inside. It's got a number of teeth on an internal rotor, and it's got a number of windings on the inside. So you can take a look at an image like this here for a basic diagram. Rotors, the rotors have many teeth on them. Typically they have about 50 teeth. There's a shaft, there's a body, and there's magnetic windings as the stator. And there's a bunch of magnetic windings. Typically you've got, for example, for the standard types of motors that we use, we have an eight winding kind of a system with two phases. So all the motors we've been using so far and what we drive with ramps is two phases for the ramps stepper driver. You also have five-phase motors, but how? Okay, so how does this work? How do you get precise motion along an angle, like 200 steps per revolution, out of a stepper motor? Please look at the Wikipedia diagram that really explains it quite well. And essentially, you have this interior rotor. In this example here, we've got 25 teeth, and you're activating 4 coils. Okay. When you activate, what you see is that when you activate each coil, the teeth line up against one another. So that means these coils have to be offset a little bit by a fraction of a tooth from each other, so that when you energize one, you have a slight motion in a given direction. So in this example here, the way the math works out, there's 20. In this example, it's 25 steps and 4 teeth, four magnetic coils there. In the real case, you have 50 teeth and 2 sets of different coils, similar to this. So you've got 50 teeth times 4. Here, the 4 is represented by the way you energize 4 adjacent coils. So there's a pattern. You have to, basically when you turn on a stepper motor, you don't just give it electricity, you have to pulse a set of coils one after another in a sequence to make the rotation happen in an orderly fashion. way the sequence looks, typically the pulse trains that you give to them are one after another in a fashion like this. So you turn on one, you turn on another, after a little bit of time, the third and fourth, and so forth. You have a concept of micro-stepping where you're not only turning on one set of coils at a time, but partially turning on one, so giving a little bit of juice to one, and then some to another. So you have the idea of micro-stepping within stepper motors. Altogether, you get, in a typical scenario like we use, we get 200 steps per revolution with micro-stepping, and we can divide round motion into precise motion. We mentioned, what do we say for 32, where do we get from 200 to 16 micro-stepping? Well, with 16 micro-stepping, you're able to get even finer divisions of 3200. Is that how it works? Are we actually dividing the 200 steps further into 16? It seems like that. Yeah, that's what we're doing. Yeah, by energizing partially, so that yeah.
So you can get extremely micro precision.
Yeah, very high precision from these stepper motors. But now with the full stepping, you get the most strength. With the further and further micro stepping, you get less torque that you're able to hold. Right. So the idea there is within stepper motors, you have a holding torque. When stepper motors are stationary, when they're not moving, they can hold the most. They can hold the most torque. Once they start moving, you're partially energizing one coil then another. So actually the torque goes down, and the torque curve goes such that your very high torque to about 500 RPM typically. So this is a typical kind of a RPM curve for a stepper motor. Torque on the left axis versus speed. So you're about full power from 0 to 500. Then you see a gradual drop, but you can go quite a bit down to 20% of the torques up to say like 2000 RPM. So it's still pretty fast, but you get the very useful torques, higher forces at the much lower RPMs. On ramps, we implement micro-stepping. So the very practical thing is, you see this is a ramps board, and on ramps you implement the micro-stepping by putting in jumpers. So it's either 1, 2, or 3 jumpers that correspond to half, quarter, 16th, 8th, and 16th micro-stepping, depending on which jumpers you put in. In our case here, we use all the 3 jumpers, and it gets us 16 micro-stepping, which is the limit of the ramps board. So the stepper driver, what it's doing, it's creating a set of pulses at varying time intervals when you have micro-stepping. So there's a little microprocessor on board each of these stepper drivers, which allows you to do just that. So it's not, you don't just plug in a stepper motor into the wall, you give it a finely controlled pulse sequence, and that pulse sequence is controlled by Marcin. Marcin gives the stepper drivers basically step, direction, and enable signals. And how do you control the speed? You control it by how fast you're switching the poles. So the speed function, that at that level, the stepper drivers interpret. They give you the pulse sequence, but the actual speed, all you're giving to the stepper driver itself is just stepping, enable direction at. No, I'm actually not sure about that. Who is doing the timing for the particular speed? Is it the Arduino that's saying, oh, now turn it on and off? Or is it that
through the prolonged this coordination, the Arduino sends a certain...
Isn't the G-code, isn't the speed in the G-code?
It's in the G-code. The G-code is interpreted by Marcin, by ramps. The speed, right, you set the speeds in...
The Arduino has a interrupt to ensure very precise timing on the operations, and I think some of them are high frequency.
Yeah, you just give it the speed. I believe after you declare a speed, the stepper driver, the Arduino sets the speed, and the stepper driver actually executes that speed by the appropriate timing sequence required to get that particular speed. So that's kind of the insights of how that works. If you ever wanted to build any of these, I mean, it's a bit complicated,
The code is
I would
open
say,
source, and you can take it apart.
but you can examine it
It is
and see what it is under the hood of this system. In the OSE, like getting to very practical aspects of this, with the OSE universal controller, we've got the ramps and the screen and power supply and plug and other components. We can, the power of the universal controller is that you can plug in either your small little Pololu style stepper drivers here right into the board, or you can use bigger ones. We mentioned that you only need three properties. You need the enable, step, and direction signals. So underneath, from the Arduino, you're only using 3 pins underneath these stepper drivers. So each stepper driver just to show a picture of these drivers. So each of these is a small little chip like this, costs $1 or so. So that's our individual stepper driver with the heat sinks on top. What you see for the metallic object there is heat sinks, because that's the microprocessor there gets a little hot. But these are quite accessible. You can, if it breaks, if it burns out, you can replace it. It's a modular system. But the power of this comes when you plug in external stepper drivers. So let's talk about how that is done. So let's start with options that you already have that fit in that form factor. So right now off the shelf you can also get these other Pololu-like stepper drivers. These are the TMC2208, same form factor, but their advantage is they actually provide silent operation, so you do not hear the stepper motors humming and making music. It's pretty silent. There's another option, the advanced, even more advanced stepper drivers. These are called trinamic. These are clones, but trinamic stepper drivers, where also the same form factor gets you additional properties. You can actually measure the current that the stepper motor is taking, and it can allow you to remember where you were. So if the power goes off, you can continue where you left off. So the usefulness here, one, is that you can have silent operation. Two, you can have the ability to use the stepper motor itself as the end stop sensor. Basically, when you hit into the limit of where a given axis can go, you detect a higher current, and you're actually measuring that instead of using end stop. So this allows you to use one less component in the 3D printer or universal access system. So that's very useful. It would be something good to develop on our side if you want to replace, just remove the need of using end stops, which take you a little bit to fabricate and put on. It's less parts the better. So put more logic into the electronic components instead of additional components, new ones that, as opposed to ones that already exist that you're using. So you're using the stepper drivers already. It's like having a built-in end stop, which is awesome. And that's a common feature these days. That came out maybe a couple of years ago. Right now a lot of people are using that. We haven't implemented that yet. But now the power comes from using larger stepper drivers. So take this much larger current handling. The small steppers, they get you up to about 1 amp of current. You can buy external stepper drivers that get you up to 4. These are 4, so they cost 4 amps of current, up to 50 volts. So you're talking about $11 for one of these off Amazon. And you can have these that are larger and larger. These are just particular ones that are good enough for the larger NEMA 23 motors that we're using, the high torque 425-inch ounce motors that we're using on a 2-inch universal access system for the heavy duty mill. These are sufficient for that kind of level of operation. You can get larger ones as well. But how exactly do you connect them? You want to take a look, start looking at getting familiar with the ramp's wiring diagram really looks like. So here's a simple way. So the stepper drivers are taken off here, and you use 3 pins off the actual stepper driver connections, which are enable, direction, and pulse or step. So you're essentially connecting 3 wires plus a 5 volt to the stepper driver, and then on the other side of that, the other green terminals here, you're connecting your stepper motors through 4 wires. So these are simple bipolar, the 2-phase stepper motors, phase A and phase B. And then you also have voltage and ground. So that's you would have a power supply connecting to the other side of this external stepper driver, which in this case, these are actually up to DC 9 to 42 volts. So you can run your stepper motors up to 42 volts. That means you get higher speeds. Yeah, the higher speeds at higher voltage refer to one of the properties of the stepper motor, which is its inductance. There's both resistance and inductance in a stepper motor. The higher voltage you can push through, the lower the inductive effects. In other words, you can get it up to speed faster, and therefore you're able to achieve higher speeds, because at a certain point you get back EMF from the coils, and that back EMF reduces effectively the voltage you're applying to it. So if you have higher voltage to push, you're effectively can drive a stepper motor faster. So where we looked at a speed diagram of when we look at the torque curve, which refers to the speed, really the effective speed of a stepper motor, this here would be at a particular voltage, like 24 volts DC. Initially we used 12 volts on our ramps. Right now we're at 24 volts, but if you got this up to say 40 volts, maybe the curve would be perhaps a little higher. So you'd gain something, I don't know exactly how, but if you can Google dependence of stepper motor speed torque on voltage, and you probably get some curves here that show that at lower voltages you can only go so fast with a given stepper driver. So you look at images, and actually, yeah, I wasn't really able to find. This is one of those things. I wasn't able to find good curves on this, and they're kind of hiding somewhere. But this is definitely true, and I guess not a lot of people are publishing data. This looks like something like it, where you would have like higher voltage, you get faster speeds. I'm not sure that's exactly what that is, though. Not sure. But the higher the voltage, you're able to achieve higher speeds, and that will matter when you're pushing the performance, if you're pushing the performance of your machine that you're designing. So ramps in general, what's the ramp schematic? We should get familiar with this since we use this all the time. So that's your ramps. Basic wiring here. So the stepper drivers go into all these sockets, the 2-row sockets, which you see 5 of them. The actual plugs for the steppers, where you plug the stepper motor wire to the stepper motor, are these ones in green, a set of 4. So in our case we're using an extruder, we're using the X, we're using the Y. We're actually taking the extruder 1 and using it as the second Y, since we have a 2Y axis system. So that's we've done that in Marlin. So that's configuration advanced in Marlin, that you can change that so that instead of this being the extruder, it's another Y axis.
I noticed on your printers the end stops are the 1st, 4th, and 5th channel.
Yeah.
Why not 1, 3, and 5? That's what I've had on.
That's typical. Yeah. However, that depends to minimum or maximum locations.
So you've got one on maximum.
Yes, we do, because
Which
the
is
Y.
Maximum Z.
No, it's maximum Y. You see the end stop is on the far side, which is positive Y.
That's why. Okay.
Yeah. So it's going to be 1, 4, and 5. Because Z is actually minimum. Minimum being the minimum distance from the bed.
Okay, that makes sense.
So it's 1, 4, and 5 for where we plug in the end stops for the D3D motion system, for the 3D printer. So there's the locations of the jumpers. I mentioned that you set the microstepping. We always use 3, where we use 16 microstepping. Some other things, the LCD display plugs into these long rows here. There's power. So in our current system, we're plugging in 12 volts into the upper connector, and we're changing this 12 volts at the bottom to 24 by removing that diode right there. So we're hacking our system to ramps on 24 volts DC, and you can see that on the wiki. Ramps on 24 volts is the wiki page where we show exactly what are the modifications to the system in order to run that. So it's a simple diagram of how we're wiring up the ramps in our case, where we're plugging in both 12 and 24 into the ramps, because for 12, where do we use the 12? I don't even know where we use the 12. Where are we using the 12? I know we use everything pretty much on 24 because the fans, the heater, everything else is...
The onboard logic.
If you step in it down to 5.
Yeah, actually now that I'm looking at this, I think this looks outdated. We're connecting the 12 volts. What else is a 12 volt on the ramps? I'm forgetting now, but I don't think there is. So right now we're taking the 12 volts and we're stepping that down to 5 volts to plug that into an end stop. That's what we're doing. So we're just using, right now we're using that terminal essentially as a power source for the step down. We're using a 12 volt to 5 volt little board that we feed into the end stop pins. So I guess there's nothing on board that uses that 12 volt. No, there is. I'm sorry, there is. The one thing that does use it, the 12 volts, is the signal to the relay. So the hotbed is activated by 12 volts, which activates the solid state relay to 120 AC heat bed. So I'm sorry, yes, we do need that second connection there. And we're also using that second connection up here, so maybe we're using the second connection, the upper one, which is 12 volts. That feeds the heat bed turn on, and that we use for our little voltage step down. I mentioned that we cannot power the Arduino ramp system from 12 volts because it blows the voltage regulator, because we have the LCD and so many components on top. So we're using a reduction of 12 volts to 5 volts fed through the last end stop pins, which are empty. Through the red and black that you see here, we're actually feeding power to that, where the red is plus and the black is negative. So that's a brief overview here. But there's yeah, so ignore this barrel jack here. That turns out not to work. Okay, so going back to the design document. So that's ramps in general, but more specifically, if you ever need to hack it, you want to look at the deeper diagram that's like right here, which shows you more information about what's underneath here. So for example, under each of these double row stepper motors, you'll see, if you look at the fine print, there's the EN under the pin here, the first pin. And then when you go farther, there's step. You can read the step there, ST, and then DIR for direction. So you use this pin here at the beginning, and these two pins when you're connecting to the stepper, external stepper drivers. So that helps you. These diagrams are all over the internet. So when you pull it up, if you forget how to connect to your external Toshiba 6600 stepper driver, you can look at this for enable step and direction. And we also have done this for the CNC torch table. This is actually from Germany, from Oliver. We used a particular system here where this is how we connected it all up. You can read more details on it, but there we are not using ramps. We're using a dedicated height controller board that Oliver has designed for the open source world. So if you want to design your own controller, there actually isn't a nice beefy one. There may be some small ones, but the one that's equivalent to like a 6600 4 amps, you can see this. This is fake open source. This is non-commercial, but you can actually put... So what you do is you look at the first thing you do is you look at the license. What is this? Is this open source? Here it says Creative Commons Attribution Non-Commercial Share Alike International. So it's not open source. It's not commercial. meaning without the freedom of you to make this or selling it, which is not open source. But you can study this. You can still study this because they have the files in Eagle. So Eagle is not an open source format, which typically goes with non-open source designs. But you can study this, and you can actually mill yourself a board. It's it's got quite a bunch of components, including a big heatsink, because the switching part will require fast switching. So there's a heatsink involved. But yeah, you can take a look at the reference design here, where this design was obtained from another non-open source documented design from the RepRap wiki. So you can look at these two to see how you, if you were interested in designing your own. Yeah, so I think that's about it. For the practical applications of knowing how to use stepper drivers, we have to know that you can use either existing ones, which have the nice features like eliminating the end stops and being very quiet. So we have applied the quiet ones. They work really well. I mean, they're just quiet and it's pleasant, so you can have this in your kitchen or in your bedroom and you're not actually disturbed by it, because otherwise they just make a lot of noise for the 3D printer. If you talk about the 3D printer. So to summarize, you have also the option of using external stepper drivers, which are much bigger, much more powerful, so you can handle just about any power you like, which is great because then we can connect that back to the ramp system. Right now, off the shelf, the larger stepper drivers are quite accessible, like $11 for one, but absolutely we would want to get open source design for even larger ones, because they are going to be more expensive, as I mentioned many times. The larger you go in scale, the less mass production of it there exists, and therefore the prices typically go non-linearly expensive when you go to large components. So there is a huge case still left over for anyone who's an electronics designer to design an open source stepper driver that can be built to any size. So I'll wrap up with that. Any questions from here or the remote side? Okay, so I think we'll get going back into the workshop and do some finishing work in the Open Source Microfactory Steam Camp. Okay, thanks a lot, everybody, and we'll talk to you tomorrow again at 9 a.m. Bye-bye.